Bismillah ar-Rahman ar-Rahim. Dear students, welcome to lecture number 12 of Advanced Information Systems course. Today our topic is Ontology Engineering. We'll talk about the manual process for developing ontologies. We'll see how we can reuse existing ontology in our ontology engineering process. Then we'll talk about semi-automatic ontology acquisition, and finally we'll see how to map different ontologies to describe a particular domain of interest. These are the main stages in ontology development. These are 8 stages, but it is not a linear process, which means that many times we have to go back from one stage to any previous stage, and we may have to repeat it several times. Let's say if we are at defining properties stage, we may have to go back to enumerating terms, or we may have to go back to consider reuse, or we may even have to go back to determine scope. From here, maybe we'll go here, and so on and so forth. So it is a highly repetitive process. It's not really a linear process in which every step is completely done and then we move to the next without having to repeat the previous step again. So practically it will be a highly non-linear process with many phases overlapping with each other and having to go back and forth between several stages. So let's discuss all these steps one by one. The first thing is to determine scope. So scope is the coverage of ontology. There are many dimensions of scope. We need to decide how broad the ontology would be, how deep the ontology would be, and the level of details, how detailed the ontology that we want to develop it would be, right? So there is no one way of developing any domain. For every domain, we need to decide our own scope, our own requirement. It is just like, roughly speaking, you can consider it as the requirement specification of the software development process. Okay, so to what extent we want to describe the domain of interest, it depends on the use of the target ontology. It depends on the feature extensions. Okay, so all these things, they will decide the breadth of coverage. I mean, how many top level concepts we have. It decides the depth of coverage, like how deep we are going to go in every concept, and the level of detail, how many properties the different concepts they need to have. So the basic questions that need to be answered for determining scope of the ontology is, what is the domain the ontology will cover? Are we making an ontology for computers, or for human resource, or for university, for products? So there are unlimited number of domains. So the first question, of course, is, what is the domain? For what we are going to use the ontology? What is the purpose of ontology? The type of questions, we call them competency question. What competency questions? What are the type of questions that the ontology needs to answer, and who will use and who is going to maintain the ontology? So all these questions, they need to be answered to define the coverage of the ontology. Just to give you a small example, here is the set of competency questions for disaster management. So we have several disasters in the world, like earthquakes, floods, tsunamis, terrorist attacks, and so on and so forth. So as a part of one of our research project, we have developed an ontology for disaster management. So this is a brief set of questions that are used to define the scope of the ontology for the disaster management. Like the first question, the ontology should be able to answer, what is the location of disaster, where it occurred? What is the time that the disaster occurred? How many people are affected, injured, dead, misplaced, and so on and so forth. So for every domain of interest, we need to list down the competency questions, the questions that the ontology should be able to answer. The second question, the second phase in ontology development process is considered reuse. Well, we all know that there's nothing new in the world. Whenever we want to do anything, we always try to do a related work study. There are always some things on which you can build your work. So similarly for ontology development, we rarely have to start from scratch. There are always existing ontologies that can provide you some good starting point. We'll talk about some of the existing resources in the second part of the presentation, inshallah. So we always consider reuse. And there are many benefits, of course, for reuse. One thing, obviously, it will reduce our effort. The second thing, if we have many shared ontologies, if we are reusing them, then there is more understanding or interoperability between the ontologies, right? So the third, the chances of mistakes are less. If we are reusing some existing well-defined ontology, of course, it has been revised, it has been reviewed by many people, so the chances of mistakes will be fewer. The next step is to enumerate terms. Now we need to write down an unstructured list of all the relevant terms that are expected to appear in the ontology. So now, without any order, without any structure, we try to find out the relevant keywords or the terms in the domain of interest that we are going to describe. For example, if I'm making an ontology for students, the obvious thing that would come to my mind is the student has a name, the student has a date of birth, they have an ID, they are registered in a program, they take the courses, they take exams, they do homeworks, and so on and so forth. So all these words, they are the terms in this domain of interest. If I'm making an ontology for computers, then the relevant terms that come to my mind are hard disk drive, RAM, resolution, storage, cache, and so on and so forth. So mostly the nouns in this, they will form the classes, and the verbs, they will become the properties in our ontology in the next stage. Traditional knowledge engineering tools like lettering, grid analysis, they can also be used to obtain the set of terms, and they can help us in defining the initial structure of these terms. Structure means the concept, sub-concept hierarchy, the property, sub-property hierarchy, the relationship of the concepts and properties, some of the basic constraints. So although it is not done at this stage, but it helps us in initial structuring of the concepts, right? So just to give you an example from the disaster management, these are the terms that are of interest in this domain, like disaster type, disaster location, disaster date, effects. Now this is a verb, so probably it will become a property, okay? These are the nouns, so they will become classes, okay? So the nouns, they become classes, and the verbs, they become properties of the ontology in the next phase. So at this stage, we are just interested in unstructured, you can say a bag of words. It has no order, it has no structure. It is just the list of words that are of interest in the target ontology. Next, define taxonomy. Now the relevant terms must be organized in a taxonomical hierarchy, which means that now they also have a structure. Now we have parent concepts which have child concepts. We have parent properties which have child properties. Okay, so at this stage we are interested mostly in classes. So all the classes are organized in a taxonomic hierarchy. It means the parent-child relationships are defined to define the structure of the concepts. For example, here we can see again referring to the same disaster management domain, the thing is the topmost concept in all the ontologies. Everything is a thing, like the object class in Java. Okay, then we have a top level concept disaster, We have another top level concept: disaster date, disaster location, losses, relief items, and so on and so forth. If you go to disaster, we have two main types: man-made disasters and natural disasters. In man-made, further we have strikes, we have terrorist attack, we have transportation hazard. In transportation hazard, we have further aviation hazard, train collision, vehicular collision. So these are the top level concepts. We have some mid-level concepts, and the bottom level concepts, they are at the lowest level of the hierarchy. So all the concepts are organized in a hierarchical or a taxonomic way to define parent-child relationships. The next is to define the properties. Often it is interleaved with the previous step. Often we collected all the terms, and now when we define the terms, we segregate the terms. Now some of them, they will become class subclass hierarchy. Some of them, they will become property subproperty hierarchy. So these two steps of the class subclass hierarchy and defining properties and property hierarchy, they are pretty much tied together. And we know that what do we mean by subclass of from the RDF also, that any child concept or any child property will inherit all the constraints, all the relationships, all the properties from the parent concept or parent property. While attaching properties to classes, it makes sense to immediately provide statements about the domain and range of the properties. If you remember in the previous lecture in the RDF and RDFS, we talked about domain and range. So for every property, to what type of concepts it will be applied, and for every property, what type of values this property will have, right? So there's a methodological tension here between generality and specificity, whether we should attach the domain and range restrictions at the top level concepts or at the bottommost, but there are, it's a long debate, we'll not enter into it, but you have to define which suits the best for your domain of interest. So both have their own benefits and drawbacks. If we attach them to the most general level, then they will migrate to the lower levels altogether. But they will not be, very specific. They will be more general. But if we define them at the lowest level, it becomes more flexible, and if later we have to make any changes, we can make them quite easily. So there's a trade-off between both the options. Sometimes it is better to put the domain and range restrictions as general as possible, as higher level as possible. In some cases, it is more beneficial to put them at the lowest level to make them as specific as possible. So there is a trade-off between generality and specificity, whether to put the domain and range restrictions. So coming back to our example for disaster management, like I have two properties, disaster location latitude and disaster location longitude. These are simple properties whose domain is a disaster concept. So every disaster will have a latitude, every disaster will have a longitude, and both of them, they define the location of the disaster. So the domain of these properties is disaster, and the range is the latitude and longitude values. The decimal values, they have a typical format for lat and long values. Similarly, we have another property, requires services, is a complex property which is applied to the properties, and it has the value as property as well, right? So here it is applied to disaster concept, and the range is the services concept. So a simple property is applied. We have two types of properties. The simple properties, their value is as a literal like lat and long values, they are literal values, okay, like numbers or strings. The complex properties, their values are the concepts, okay. So there is difference between simple and complex properties. The next is the facets, or we call them constraints or restrictions. Whenever we want to describe any domain of interest in a logical way, there are many constraints or restrictions on the properties. They are of many types, like cardinality restrictions. First of all, how many values a particular property can have. For example, if I say that parent, okay, everybody has parents, so how many values we should have for everybody as parent? Exactly 2 values, no less, no more, okay. Similarly, if we have a property of ID, everybody can have exactly 1 ID, so we are putting cardinality constraint. Let's say we have a constraint on a student for registering courses. A student must register at least 1, okay, and at most, let's say 3 courses. So this is a cardinality constraint from 1 to 3. We can have any value between 1, 2, and 3, no less than 1, no more than 3. So for many properties, we have cardinality restrictions, okay. So we put them in the facets or constraints. Required values, for some things the values are required, they are not optional. For example, if there is a course, the course must have an ID. A course cannot exist without a course ID. A person cannot exist without a date of birth, okay. So for many values, we have a requirement constraint which restricts the classes to have some value, definitely have some value for those properties. Whenever we are defining an instances, the value for these properties, they must be given. It cannot be optional, it cannot be null value. Then there are relational characteristics. All these are new at the ontology level. In case of RDF and RDFS, we have only domain, range, and some data type restrictions. When it comes to ontologies, the type of restrictions are much broader and they are much finer. They give us a way to put very fine constraints on describing the domain. For example, two properties can be, a property can be symmetric. Sorry, one property, it can be a symmetric property. For example, if, let's say friend of, if A is friend of B, okay, then B is also friend of A. So it is symmetric. The relationship between two individuals through this property, friend of, is symmetric, okay. So it means any relationship of individual A with B, it is the same kind of relationship of B with A, like friend of, maybe we have colleague of, maybe we have sibling, okay. So there are many properties which can be defined as symmetric properties. It means the relationship between A and B is same as relationship of B and A. The second is transitive property. Sometimes there is a transitive relationship between the two properties. For example, ancestor of. If A is ancestor of B and B is ancestor of C, then A is ancestor of C, okay. Or descendant of. If A is descendant of B and B is descendant of C, then A is descendant of C. Or greater than. If A is greater than B and B is greater than C, then A definitely is greater than C, right? So it is transitive, the relationship of A to B, and if you have same relationship from B to C, then A to C relationship remains the same. Similarly, we have inverse properties. Sometimes there is an inverse relationship between two individuals. Like if A is parent of B, then B is child of A. So parent and child, they are inverse properties. Okay, so we can define this. Similarly, functional values, that one individual cannot have more than one value for this. For example, ID, no person can be assigned more than one IDs, or there is inverse functional as well, in which case one value cannot be assigned to more than one individual. Like ID, it is both functional and inverse functional. Nobody can have more than one IDs, and one ID cannot be assigned to more than one individuals. Or let's say email. If we talk about email, email is not functional because one individual can have more than one emails, but it is inverse functional. One email ID cannot be assigned to more than one individuals. So anyway, these are some of the kind of constraints that we can put in the ontology for very crisp, very fine descriptions of the domain. In the next stage of the ontology engineering process, we define instances. If you recall from RDF lecture, we have the domain knowledge in RDFS, RDF schema, and then instances, they are defined in RDF. Here we talk about the general things. Here in RDF we talk about the specific things. Like RDF contained information about courses, about lecturer, and so on and so forth. In RDF, now we talk about a particular course, discrete math. We talk about a particular lecturer, David Billington, and so on and so forth. So these are called instances. The instance data, or the individuals that belong to different concepts. So number of instances will be much larger than number of classes, of course. You can compare it with a database schema also. Like in database schema, we have the structure of the data, and then when we enter records, the number of records, they are much larger than number of entities. Okay. So mostly the ontology population is not done manually, but we retrieve them from the legacy data sources or from any text corpus or relational databases or any other way. So mostly we use some automated way of populating the ontology with the instance data. Most of the information is in the form of relational databases or legacy data sources or plain loose text. So we need to apply several techniques to populate the ontology with the instance data. The next is checking for anomalies. There might be any inconsistencies in the ontologies. There might be any, you can say, problems, any anomalies. The information is not consistent, it is not compatible. Different pieces of information, they are not supporting each other, they are contradicting each other. So this is one of the main advantage of the OWL layer on top of RDF layer. RDF schema provides you the basic ingredients to describe the resources or to define them. But OWL is based on formal semantics. So OWL, by using this formal semantic, we can use any reasoner. Okay, we can use any reasoner, just like our mind processes the things logically. Similarly, the OWL descriptions, they are processed logically by the reasoner, and it can find out the inconsistencies automatically. So example of common inconsistencies: incompatible domain and range for transitive, symmetric, or inverse properties. So we may have incompatible domain and range definition. Let's say there's a transitive property, okay, but or a symmetric property, we did not give proper domain and range. They are incompatible. Cardinality properties, the number of values, we have given some. Let's say at parent property, we have given some cardinality constraint, and at the child level, we are trying to violate that constraint. So all these inconsistencies, they are automatically found out by applying any reasoner on them, because the ontologies, they use the formal semantics, formal knowledge representation, like we have discussed briefly in the previous lectures, like horn logic, okay, the if-else conditions. But in ontology, mostly we use description logic, DL. Description logic is mostly used for OWL, so not the horn logic. We use description logic for defining the ontology. Like OWL is based on DL, description logic, and we have stable reasoners available to process the description logic, and it can be used to identify and remove any anomalies. This is the last step. This is the last step in ontology construction by manual process. The second topic of today is reuse of existing ontologies. There's nothing new in the world. There are always some existing works available on which you can build your own ontology on top of them. There are many examples, like in medical domain, we have cancer ontology from National Cancer Institute in the United States. Cultural domain, we have art and architecture thesaurus, ULAN. For geographic domain, we have some ontology. So for many domains, the domain specific ontologies, they are available. So if you are, let's say if you are making a new ontology for medical domain, you can take some motivation from this ontology. Or if you are working in cultural domain, you can build your ontology on top of one of these domain specific ontologies. The second is integrated vocabularies. Sometimes some people, they have merged independently developed vocabularies into a single large resource, like unified medical language system. As the name implies, it is a unified resource which unifies many domain descriptions in the medical domain, like 100 biomedical vocabularies. Mostly the semantics of these resources, they are rather low because of the obvious reason. You see, if we are integrating hundreds of resources, there will be many inconsistencies. So to agree on something common, the concepts or the semantics will be very general, very abstract. Okay, but anyway, they can always give you a starting point. You can take motivation, you can start from these resources, and you can build your own vocabularies on top of them. Upper level ontologies, there are some other general ontologies. Okay, so they are very general. They define very basic or abstract concepts that are used by many domains of interest, like time, event, space. So some very basic concepts and very general concepts, they are defined in these ontologies. IEEE, they also have a standard ontology, I believe SUO. So again, you can build your ontologies on top of these. You can take benefit from these general concepts or general descriptions of the concepts. Then there are topic hierarchies. They are not as such ontologies. They are built for different purposes, but they are simply set of terms loosely organized in a hierarchical way. It cannot be really called taxonomy, but it is a mix of different type of relationship, like is a part of, contained in. So it is more like abstract or loose description of concept, but like open directory hierarchy, it captures like more than 400,000 hierarchically organized categories, and it is also interestingly available in RDF format. But again, the resources are there. They can give you a starting point at least to build your own ontologies on top of them. And lastly, we have some linguistic resources. Again, they were not built as ontologies, but they were built to understand, define, or describe the languages. Like WordNet is one of the most famous and mostly used resource for languages, for linguistic, which defines the nouns, verbs, different parts of speech, their relationship, the brief hierarchy, thesaurus. So, and the word nets are available for many languages, English, Arabic, and many other languages. So again, you can get motivation from these resources, and they can help you in giving a head start for developing your ontology. And another is ontology libraries. So there are many ontology libraries, like one of the most famous is DAML, Dot Agent Markup Language. It was one of the earliest ontology languages, but they have a huge ontology library from which you can import the ontologies and you can extend them with your own descriptions of the concepts and properties. Next is semi-automatic ontology acquisition. You have seen that manual ontology construction, it is a tedious job. It is very expensive. It is time consuming. There is a need of highly skilled individuals. So it is not really easy to develop a good ontology. There are many machine learning techniques that can be used for knowledge acquisition or knowledge revision or maintenance task. It is not our main topic. We will not go into the details, but there are several tasks which are supported by machine learning techniques, like extraction of ontologies from existing data on the web, like extraction of relational data and metadata from existing data, like merging and mapping of ontologies by analyzing extension of concepts, to map the different concepts in different ontologies and to merge them into one ontologies, many smaller ontologies defining parts of domain, and we can merge them into a bigger ontology, or to observe the use of the ontologies and improve the semantic web applications or the hierarchy or the concepts or properties of the ontologies. So it's a complex topic. We will not go in detail. It is beyond our scope, but there are many machine learning techniques that can help us in the ontology construction process. Okay, they are called semi-automatic ontology acquisition or ontology construction methodologies. The last thing is ontology mapping. In every domain of interest, it is very rare that you will have a single ontology that will completely fulfill all your demands, all your requirements. Many times, multiple ontologies, they need to be combined together to completely fulfill your needs, to be able to answer your competency questions. Let's say if I'm making an ontology for university domain, maybe there is someone who has made an ontology for persons. So in a university, many persons are involved. I can define a student, I can define a faculty member, I can define a staff member by extending the person ontology and reusing the concepts that are defined as a person. Every person must have a name. Every person has an address. Every person has date of birth, and so on and so forth. So if there's an ontology of persons, it is already there. Why not reuse it? Why to reinvent the wheel? Okay. So whenever we are building our ontology on top of some ontologies, there is always the problem of ontology integration. How to integrate our ontology with those ontologies, or how to align our ontology with them, or how to map the different concepts in different ontologies to really come up with the similarities. So there are many approaches for ontology mapping or alignment, or we call it ontology integration. We'll talk briefly about 4 of these approaches. We have linguistic approaches, there are statistical, structural, and logical approaches for ontology mapping. Again, it is beyond the scope of our course to go into the details, but we'll quickly see what are these techniques about. Linguistic methods. The most basic method to try to exploit the linguistic labels attached to the concept in source and target ontology to discover potential matches. So we have a source ontology and we have a target ontology. So we simply look for the linguistic labels. Okay. So it can be as simple as stemming. Okay. All of you have studied in the previous lectures in IR. We can stem. Every word has a root word. So maybe we have used different forms in different ontologies. So if we stem them together, if we stem all of them, now we can see the matching, or we can calculate Hamming distance. Like if we convert a label into individual bits, now we can compare the bits and we can see how many bits are different. Hamming distance we can calculate, but it is a tricky thing. In many cases we need to use specialized domain knowledge to really find the similarity between the concepts. Like a simple example given over here is diabetes type 1 and diabetes type 2. So there is huge difference. Any medical doctor will tell you how much difference is there in diabetes mellitus type 1 and diabetes type 2. But if we take a Hamming distance, they will come out to be very, very close. So if we simply calculate Hamming distance, we will say that they are same concepts, but actually they are extremely different concepts. So anyway, in certain cases stemming might work, in certain cases Hamming distance might work technique, and in certain cases we need to have specialized domain knowledge to really map the concepts together, but these are different ways. There are statistical methods. Some methods they use instance data to determine correspondence between concepts. A significant statistical correlation between the instance of source and target concept gives us a reason to believe that these concepts are studied. So if we have a significant statistical correlation between different terminologies, then we can say that they are statistically they are same, so probably linguistically or ontologically also they are same. This is one way. Then there are structural methods. In every ontology we also have a structure of the ontology, which means like the parent concept, the child concept, parent-child hierarchy, the properties linking different concepts together. So an ontology has a complete structure. Actually we have seen that the ontology is like a directed graph. Okay, if you recall from RDF is also ontology. So it is a directed labeled graph in which every node is labeled and every arc is labeled. So it has a well-defined structure. So we can compare the structure of two ontologies and then we can say whether they are same concepts or not. A simple example is, let's say if you recall, when we are talking about motivation for semantic web, we talked about the pipe concept. So let's say we have pipe concept in two ontologies, and one is in computer science domain, so it will be linked with terminology from computer science domain. Another one, let's say it is in the volcanic domain, volcano pipe, so it will be related with the terms from volcanic eruptions. So when we see the structure of the ontologies, now we can clearly see that they are not same. They are basically homonyms. Okay, they are homonyms. Same word is used in different concepts. But on the other hand, if we say that all the concepts that are used in this ontology with this pipe, most of them they are also used here in this ontology. Let's say 9 out of 10 or 8 out of 10, they are the same concept, same kind of properties. So now we can say that, okay, because the structure of both the concepts is pretty similar, we can say that they are the same concept. It's not only about the label, they are not homonyms, but they are in the same domain of interest. Then the last is the logical methods. It is the most specific to mapping ontology. As we have seen before, that ontologies, they use formal semantics. Okay, like just now I told you that OWL, it uses description logic, DL, okay, and any reasoner, description logic, DL. So any reasoner, it can process two ontologies logically, okay, and then it can find whether they define the same concept or not. There is a serious limitation of this approach, that many practical ontologies are semantically rather lightweight and thus do not carry much logical formalism. Well, it will work only if the ontology is defined at a very fine level with deep and refined descriptions of the concept. But many ontologies nowadays, they are lightweight. Lightweight means they are just like taxonomical hierarchies. They are like taxonomies, okay. They just capture the parent-child concept and they do not put all the logical constraints on them. For these logical methods to work, we need the logical fine constraints to be put on all the properties and concepts. If we do not have those logical details there, then the logical methods will not work. So to conclude, we can say that there is much potential and there is much need for semantic web engineering, but it is not a well understood area yet. There are a lot of research projects going on. There are a lot of works that are in progress, but we need to have much more progress in the coming years. So there are no like off-the-shelf techniques that are available, and probably hopefully it will change in future, and we will have more standards, we will have more refined and more elegant or more useful ways of defining the domain of interest. So at present, the ontology engineering, it is a highly technical work. It is it needs huge competencies. It is a time-consuming task. It is a highly tedious job. But in future, if these technologies they have to really take off, we expect a lot of tools, a lot of off-the-shelf tools, frameworks, and techniques there to help the users in defining their domain of interest for many applications. So this was all about ontology engineering, and we have seen how we can construct the ontologies manually. We have talked about the reuse of ontologies. We have talked briefly about the semi-automatic construction, and finally we discussed the ontology mapping problem. But there are many challenges, there are many problems that are waiting for the solutions. And if you review this lecture, if you watch it carefully, you will find that there are many research issues, there are many interesting topics of interest for research, and you can build upon them for your research work, inshallah. So inshallah, in the next lecture, we will compile all the knowledge together that we have discussed in the last few lectures, and we will see how the semantic web applications are developed by using all these layers of semantic. We have talked about XML technologies, we have talked about RDF, RDFS, ontology, and logic layer. So now, inshallah, in the next lecture, we'll see how to put all these layers together to develop the semantic web applications that can make this dream of the agent-based web and the intelligent web possible. Thank you very much. See you, inshallah, in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.